So in this presentation, what we're going to go through is what we call the data center PTP profile. So my name is Michel. I'm a network engineer at Facebook. I think early on this morning during the TAP kickoff meeting, we basically shared that there were several vertical industries that, have a need for high accuracy and reliable distribution in time and frequency across the packet networks. Each of these vertical industries have their own different use cases, but one thing that is common across them is that they're all, using IEEE 1588 or PTP, and each one of them has developed what we call or specify what we call the concept of PTP profiles. And this presentation is going to go through, what is a PTP profile and provide some concrete and technical examples of, what is generally specified within these PTP profiles. So what is a PTP profile? At the end of the day, it's essentially a document or some kind of a portion of a document that basically specifies the different type of PTP features in the various what we call attribute values in the context of a particular application. And this is generally done following various guidelines that are specified within the IEEE 1588 standard itself. The idea of a PTP profile is to use whatever is necessary from the standard to and specify this such that you can operate a PTP network that will provide some level of interoperability and will achieve various levels of performance for a particular application. So view 1588, the standard itself as having a lot of mandatory type of requirements as well as various optional type of requirements. And you can basically use whatever you'd like to develop, your own specification for your own particular application. Within the timing appliances project, we have 4 work streams that was presented this morning. OCP TAP work stream 2 is about defining a PTP profile for the purpose of distributing and synchronizing time within a data center and to serve certain time-sensitive applications such as distributed database systems, what we've heard as an example from our colleague Georgie earlier on this morning for me, by the way. When you look at for instance, synchronization, what is there to consider? In a lot of discussions, we tend to gravitate a lot in talking about PTP with respect to performance, right? Microsecond, nanosecond, picoseconds, and so on. But it's a lot more, broader than this. When you want to deploy a synchronization network, there are a lot of things to consider, such as the topology aspect, right? So very similar to like in routing, you want to prevent what we call synchronization loops, for instance. So you need to have a way to basically come up with a synchronization topology over for instance, like a routed network. You want to consider things like, for instance, maybe redundancy or using schemes like active-active or active standby, such that if a portion of your topology or elements of your topology fails, then you've got some backup or some standby embedded within the topology. From a performance, I think there's been a couple of talks this morning, with respect to what are the time error budgets or what are the requirements of the application that are necessary. Usually when you dig into this, you also have PTP as a packet protocol, so it's got a message rate associated to it that is also important to determine what will be those message rates. You generally have what we call servos, which brings about a filter design. From a communication point of view, 1588 was originally specified to use over a layer 2 network using multicast. But we know that a lot of the networks are not layer 2, and a lot of the networks do not support, for instance, multicast. So there are optional clauses within the standard that allows you to run PTP using unicast. The interesting thing here is that most of the profiles that have been developed in the industry rely on multicast. But here in the data center, we will see that there is a need to use unicast as opposed to multicast. A lot of the PTP profiles also use Ethernet as the transport between the various clocks. But again, in a data center, for instance, IPv6 is predominantly used. From a configuration point of view, PTP has a sizable number of various values that need to be configured within its own data sets, and those parameters and their values, they're different whether you're looking at transparent clocks, boundary clocks, and so on. From a deployment point of view, it's very important to look at the various elements of that synchronization network and how you're going to, rack and stack all of these elements within a data center, right? Which might be totally different than what is used in other verticals like telecom or industrial and so on. The interface speeds also from a deployment point of view or in a data center are very likely going to be different than in other verticals. And things like fiber asymmetry also, are important to consider. And last but not least, the operations aspect of a synchronization network. So how do you manage faults? How do you, monitor the performance of that synchronization network is as important. What we're going to be doing in the definition of that PTP profile is come up with some kind of a reference model that will be used to guide the development of that PTP profile. So here, for instance, we're decomposing that reference model into three parts. The top part is what we call the reference layer. This is where you would have rooftop antennas, cabling, your GNSS or GPS system. You would have your primary reference clocks. In some cases, you might want to use some cesium backup, some rubidium, and you've got the measurement ports also at that layer to make sure that whatever is coming in from the GNSS system or these reference clock is as working as expected. Then we've got that second layer, which is that middle layer in that diagram, which we call the network fabric layer, where there's a large set of network elements that are PTP aware. And PTP aware means here that they embed the transparent clock or boundary clock or some other type of clock functionality, deployed across this whole data center fabric. And then the bottom layer is what we call, for instance, a server layer. This is where you have a very large set of PTP ordinary clocks that recover time coming from the network and basically pass that time to the upper applications, right? So we've heard talks from our colleague Georgie and our colleague Dotan about the challenges also within that layer, within an ordinary clock, to actually pass that that time reference to the upper applications. So I thought it would be good to, like I mentioned earlier on, we tend to talk a lot about, you know, PTP and, you know, gravitate towards performance numbers. I thought it would be good to go through a couple of examples, you know, as to what is behind PTP besides just performance numbers. But let's start with the performance numbers, or what we consider here this time error budget. So again, we've got the three layers: the reference layer, the fabric layer, and the ordinary clock layer, or the server layer. And once you start decomposing that, you can start putting you know, numbers at various places of that synchronization network. For instance, at the top, we've got that GNSS system and what we call the PTP GMs, or the grandmasters. And there you can start saying, okay, for instance, the time error of that GNSS system, or that GM with respect to a reference, and here the reference is TAI, or the, you know, the source of truth of time, which is stands for in French, it's temps atomique international, must be within, for instance, 100 nanosecond. And here we're not, you know, inventing a number. We're just basically borrowing that number that, you know, that comes from the telecom industry, that has done a lot of, you know, a validation. I've done a lot of simulations to come up with that number of 100 nanoseconds as a budget for that, for those network elements that sit in that reference layer. And from there, you can say, okay, well, if a, for instance, a grandmaster has a, or a GM has a budget of 100 nanoseconds, then it means that any two GMs, and this is what you see on the right-hand side, any two GMs, any two GMs must not have an error more than 200 nanoseconds, right? Because one GM could be at minus 100 per definition, and the other GM could be at plus, you know, 100 nanosecond. Therefore, you know, any two GMs, you know, will always be within 200 nanoseconds. If we go to the bottom of that picture, this is where, for instance, where we have these ordinary clocks, the difference between any two ordinary clocks, you know, there's a very large set of ordinary clocks here. If you pick two out of these, any of these two here, which is TOCJ minus TOCK, must be less than 5 microseconds, which means that if you look at one ordinary clock compared to that reference TAI, must be you know, below 2.5 microsecond. So anyways, essentially here what you can start doing is putting numbers, and these numbers, or that budget, becomes very useful once you want to, either in a lab or in a production network, start you know, measuring the performance of that synchronization network at various measurement points within that that network. Another example of a PTP, like I mentioned, for instance, is this aspect of a multicast and unicast. All except, you know, one profile within you know, the various verticals uses unicast. So telecom, for instance, they have one of the profile that uses unicast. All of the other ones are multicast. So essentially, in this example, what we want to show is there is a clause in 1588 that allows an ordinary clock to request what we call a unicast service from a GM. And it does so by using a set of what we call signaling messages, where the server, or the ordinary clocks here, in that signaling message can say, hey, I'm interested in having that unicast contract with this particular GM. and I would like to have that unicast contract for X amount of seconds or X amount of minutes or X amount of days. And I would also like you, for instance, the GM, to send me 16 messages per second. So there's a lot of functionality that exists within PTP to request, those services using different rates, different durations, and so on. So here we show, for instance, that handshake of signaling. We show the grandmaster, for instance, starting to send announced messages. These announced messages by the GM are, important messages. They are not the sync messages that contain the timestamp, right? We've heard this morning about hardware timestamping and so on, and the messages carrying those, those timestamps for the purpose of recovering time. But the announced messages have a different purpose. They are there to provide information across this synchronization network about what is going on, for instance, and mainly around the quality of the various clocks, and making sure that the ordinary clocks are traceable or synchronizing themselves to the proper network elements with the highest accuracy possible. As part of, for instance, this unicast discovery and negotiation feature of PTP, you can also, once an OC, for instance, if you tear down an OC or an ordinary clock, or you want to stop the service, you can basically advertise that to the GM and say, I want to cancel my service. So there's a lot more that within that unicast discovery and negotiation feature of PTP, but I thought it would be good to share this this morning. Another aspect also is the best clock selection. So picture a diagram here that at the top of the layer, we've got this these active and a standby mechanism. We've got the data center fabric, and we've got a large number of OCs that are grouped with what we call a unicast master table that are pre-populated, where the OCs communicate with the active GMs or the standby GMs. Two more slides to go, Elad. Clock class is another aspect also where you can use the different attributes of PTP to create what we call an active standby type of synchronization network with various holdover capabilities and failure conditions. Linux PTP is one thing we are looking at to go from the specification to the implementation and configuration, and where you parameterize all of these parameters with the various specific values. Last slide. So the call for action is whoever wants to get involved into that data center PTP profile, you can do so. It's part of what we call workstream 2. And we hope to release version 1 by end of the year. Thank you.
Sure. This was great. Yep. Very exciting. We have a list of volunteers already lined up for workstream number 2, and we're looking to add more. So guys, we hope to see you all there.